pendulum formed from a ball of mass m on a string of length L. As figure shows, a peg is H is equal to L over 3. I'm sorry, I lost my spot. A peg is height H equals L over 3 above the pendulum's lowest point. From what minimum angle must the pendulum be released in order for the ball to go over the top of the peg without the string going slack? So I don't necessarily understand what they're asking.
Okay, let me draw a little picture here. You got a ball on a string, length L, mass M, swings down, and there's a peg right here. This is L over 3. So what happens when it hits the peg is so if you're swinging a ball on a pendulum and then you like catch it with your finger, think about like people doing really crazy yo-yo tricks where they like put their hand in the string and like swing around and stuff and it swings faster. So at this point, this yo-yo suddenly goes in a smaller circle, right?
Mm-hmm.
So the string would be like this. And as it comes around, if it's going fast enough, it'll swing right around the top of this peg, right?
Mm-hmm.
So it'll come and it'll just swing right over and then kind of just wrap around the peg. So they're asking, that's the ball right there, mass M. Oops. So they're asking what's the minimum angle here that you have to swing it from in order for it to swing down and then catch that peg and swing all the way around.
Okay, cool. Thank you, because I couldn't see it. But the yo-yo trick helps.
Yep.
Okay. I guess we would go from, we for sure will go from energy, and then from energy I would think we would put into kinematics.
Now it turns out you can solve this problem just purely with energy and in one step.
Okay, let's do it. So we know that at the first point we have all potential and no kinetic.
Mm-hmm.
And at the second point we have kinetic and potential.
What's your first point?
My first point is before I let it go.
Okay, and then what's your second point?
At the kick.
So here?
Yeah.
Okay, perfect. So it could be like something that somebody with this kind of a problem, what it might kind of seem like you should do would be break it up and do it here again, like find the energy here and then use that to find the energy here.
Okay.
Because the radius of the circle changes, right?
Right.
But you don't have to do that. So the reason you might want to do that is because you're like, oh, well here the radius changes, so I've got to redo my energy equations. But the energy equations don't care what the radius is.
Okay.
So the energy at this point will be the same as the energy at that point, and you can solve for either one.
Okay.
And then, you're right, this one has just potential energy. The other thing that might mislead you is if you said this only had potential energy.
Which I didn't.
Right. You know it has kinetic energy. So, why would this still need kinetic energy?
Because it's still moving, it still needs to go, it still needs to keep going and go circle around the keg.
Right. So if it catches that little peg and then comes up over the top, and it stopped at that point, it would just drop. In fact, it wouldn't even quite make it to that point because it would fall too early. Okay. So you have a height 1 equals mg height 2 plus 1/2 mv squared. So now how do you use that to find theta?
We have height 2. We need to find.
Okay, let's list a couple of these things. So what's height 2?
Height 2 is L divided by 3.
So that's the height to the peg. How high is it to the actual mass as it swings around the top?
L minus L over 3.
That would be this. It actually is that. But if this was something different, it wouldn't work out that way. So that would give you this length of the string here. So what if we take, so you know it's going to be L over 3. So you start with L over 3. But then what's this distance?
That's still L over 3.
Right, because that's how much string you had that caught this peg and then swung around. Now it's up here.
Right.
So it's just 2L over 3.
Oh, wow.
So say this was L over like 5.
Mm-hmm.
Then saying L minus L over 5 wouldn't work because that would give you 4/5, when really it's only 2/5.
Why would it just be 2/5?
So you know that you have this distance, L over 5, to the peg, and then the string that wrapped around and is above the peg now, how long is it?
If that's 4/5, then
Well, if this was just 1/5.
it would be 2/5.
Yeah, so it would come around and you'd have 1/5 above. So up to the peg is 1/3, and then that piece of string that swung up around is 2/3, or is 1/3 as well.
You know it's the same string.
Mhm.
I see it.
Right. Now, if they made this if they made this like really big, then it wouldn't work that way anymore because some of that string would get wrapped around here, right? But we're assuming it's a tiny, tiny little peg that got caught on and wrapped around.
That's cool.
Okay?
Okay.
So there's your height 2.
And then my height 1 is equal to L minus L cosine theta.
Perfect.
My mass 1, I don't know what it is.
The mass is the same for all of them, right?
And so it'll cancel out.
Yeah.
And we know gravity,
Yep.
but we don't know velocity. So, okay, would I have to break up my velocities into components?
No. So we talked about how in order to get around the top of that circle, it has to be moving some minimum speed, right?
Mm-hmm.
So what's the slowest that that string can wrap around and have that ball go over the top?
That's what we're solving for, right? No, we're solving for theta. The slowest, I don't know. Can't be 0.
No, it can't be 0, because if it was 0 at the top, it would drop, right?
What if the tension is 0 at the top?
The tension's 0, yeah.
Okay.
What is that called when as you come around the top, the string goes perfectly slack and then swings back around?
Pendulum.
So if you drew the free body diagram, originally you had, if you were going fast, you would have the force of gravity and tension, right?
Mm-hmm.
But we slow down slower and slower and slower until there's no more tension.
What do you mean, why? How do we know that we did that?
Because this is circular motion, right?
Mm-hmm.
So this would be your forces in R would be equal to tension plus mg, and that equals your mass times your acceleration in R, right?
Mm-hmm.
Well, what's another way to write the radial acceleration?
velocity squared over A?
Over r, yeah. Velocity squared over r, the radius. So that's if you have tension in the stream. So the faster you go,
Where did the tension go though?
we just slowed down. Okay? So the faster you go, the more, because this one won't change, it has to stay as mg. That's just the weight of the object, it can't change. But the faster you go, the more tension you need, right? To make up for this will get bigger as you go faster, so you need to add more tension. So if you slow down, which one do you subtract?
The tension.
Yeah, so you start making tension smaller and smaller until finally it's zero.
Oh, how did the tension turn to mv squared over r?
Oh, because that's your sum of forces. This is a free body diagram. And you have your tension.
Right, but there's no there's no tension in the equals part.
Right. Because these are your forces.
Mm-hmm.
So you have the force in your radial direction equals mass times acceleration in the radial direction.
Okay.
This is critical speed. Do you remember talking about critical speed? That's what we're talking about right now. If you want, so if it's still like unclear after this, let's see here. Then come back to this. Right here. So section 8.4.
Mm-hmm.
This is how explaining critical speed. Does that make sense?
Mm-hmm.
So this is where this is coming from. It works the same way for a roller coaster loop as it does for string. So you see what it's talking about here. You have a normal force and gravity as you're going fast. Then as you get to the critical speed, only gravity holds it. But then as you go slower than the critical speed, the normal force becomes zero sooner, and then gravity starts to pull you down.
Okay.
So what's happening as the minimum speed that it can go around the top of this is when tension is zero, right at the very top.
Mm-hmm.
And so that leaves you with mg equals mv squared over r, right?
Mm-hmm.
Can you go any slower now?
No.
No, because we got rid of all the tension and we can't change gravity.
Right.
So if we go slower, then we're not in circular motion anymore. Okay?
Okay.
So mg equals mv squared over r. Your m's cancel. So the square root of rg, that's your critical speed. That's the minimum speed that you can go around the top of a loop without falling off. That's always how it is. It's always the case.
Okay.
So you don't always have to derive it like this. If you remember that the critical speed going around the top of a circle, the slowest you can go is the square root of the radius times gravity. Always, no matter what.
Okay, makes sense.
So how fast does this have to be going as it comes across the top?
Square root of r times g.
All right. So velocity has to be square root of rg.
Mm-hmm. Velocity squared is just rg.
Yeah. So now we know gh1 equals gh2 plus 1/2 rg. All right.
And we're solving for theta.
Yeah. So let's put in our h1 and h2. Oh, actually, before we do that,
Okay.
what do we have in every term now?
We have g's.
To get rid of those. So h1 L minus L cosine of theta. h2 is 2L over 3 plus 1/2 r.
So now we would subtract L from both sides.
Hold on a second though.
Okay.
So L is a given value. We know what L would be.
L is 1, or L is whatever.
Yeah, it turns out it won't matter, but what about R?
R is the radius. I always think R is L over 3.
Yep. So let's replace that so we have it all in. So now we have everything in theta and L.
Okay. So now I would subtract this L over.
Okay. So L cosine of theta, negative L cosine of theta equals 2L over 3 plus L over 6.
And then I would divide by a negative L. And then take the cosine inverse of that.
So let's see. The inverse cosine of what do we have here? Negative 2/3 minus 1/6 plus 1 equals theta.
Where did you put you cross out all your L's?
Oh yeah.
Because we had an L in every term.
Yeah, you divided by negative L, remember?
Uh-huh.
So every term has an L in it, and they just go away.
Oh.
So negative 2/3, that's negative 4/6. So negative 5/6 plus 1 is 1/6.
Mm-hmm.
So the inverse cosine of 1/6. Is that right? No. Oh, yeah, that's right.
Calculator. Cosine. Oh, wait, I should be able to do this in my head.
Of 1/6?
Yeah.
Probably not. Pi over, no, wait.
80 degrees.
Okay. Is that a 1/6? Yeah, I don't know if that's one that you should know off the top of your head. Pi over 6, the cosine of that is, I don't know. Maybe it is, maybe not.
Yeah, it's 80 degrees.
Just straight 80?
80.4.
Okay. Now, if you think about that, is that a reasonable answer?
Yeah.
So you have to bring it up almost vertical, almost horizontal before you let it go in order for it to swing all the way around. Cool.
Yeah, finished 10 minutes early. I wonder if I could do the quadratic on this thing.
Yeah, you can. There's a polysolve function.
Where?
So, let's see. I've done it where, okay, so you can do y equals, you plug in your equation and then you do calculate the zeros. Those are the roots. Or there's a math solver. So 0, so you just put in your equation.
Mm-hmm.
So that's just the math button. It's the solver.
Cool. And I put my equation in and it'll spit out an answer?
Yeah, it'll give you the 2 roots for it. And that'll do anything. That'll do, I think, up to polynomials to the 5th.
Oh, that's cool.
So if you have just anything you need to solve, you can put it in there and it can solve it.
Thank you for your help.